Content moderation at scale isn't just a binary toxic or not problem. Modern platforms need fine-grained judgments. Is the content offensive? Does it target a specific person or a group? And how do we structure our models to handle this hierarchy efficiently? Today, we're diving into a rigorous comparison between two dominant modeling paradigms for hierarchical offensive language detection: cascaded decomposition versus joint multitask learning. We'll look at the architecture, the math behind loss functions, how class imbalance actually plays out in practice, and why intuition-based hyperparameter tuning often fails. By the end, you'll have a clear, quantifiable framework for choosing between accuracy, parameter count, and inference latency in hierarchical NLP systems. Let's start with the task structure. The standard benchmark here is the OLID dataset, which uses a three-level annotation scheme. Level A determines if a post is offensive or not. Level B, only applied to offensive posts, checks if the offense targets an identifiable entity. Level C, only for those with identifiable targets, classifies the target as an individual, a group, or other. This creates a natural hierarchy, but also a severe class imbalance problem. Level A is roughly 2 to 1, Level B jumps to 7.5 to 1, and Level C sits around 6 to 1. Most prior work handles this imbalance by guessing. They pick a loss function based on how skewed the data looks. But does that actually work? And more importantly, when you have a hierarchical structure, should you train 3 separate models that pass samples down a pipeline, or one shared model that predicts everything at once? Until now, there hasn't been a direct, controlled comparison measuring accuracy, parameter count, and inference latency side by side. The paper addresses this by building 2 systems under identical experimental conditions. First, the cascaded architecture. It uses a shared BERT backbone to extract semantic features, but each of the 3 levels has its own independent classification head. During inference, the output of level A determines whether the sample even proceeds to level B, and level B gates level C. This means a non-offensive post only requires one forward pass, which naturally lowers average latency. But it also means an early-stage error is permanent. If level A misclassifies an offensive post as safe, the downstream models never see it, and that mistake propagates through the entire pipeline. Second, the joint multitask control model. Here, the encoder is shared, and all 3 classification heads receive the exact same CLS representation simultaneously. The big engineering challenge here is that level B and C only have valid labels when their parent conditions are met. To prevent the model from learning from invalid labels, the authors introduce a task gating mechanism. The joint loss is calculated as L joint equals LA plus LB times MB plus LC times MC, where MB and MC are binary masks based on the ground truth of the upper levels. This ensures gradient updates only happen on valid hierarchical paths, making the joint model a fair architectural control. Now let's talk about training. Class imbalance isn't solved by a one-size-fits-all loss function. The authors test 3 options: standard cross-entropy, class-weighted cross-entropy, and focal loss. Crucially, they don't just use a scalar alpha for focal loss. They vectorize the class weighting, so it matches the inverse frequency scheme of the weighted cross-entropy, allowing a rigorous comparison. They run a controlled ablation across all 9 configurations, isolating random seeds to prevent cross-configuration bias. The result? Intuition fails. The optimal loss isn't always the most complex one for the most imbalanced task. Levels A and B actually perform best with class-weighted cross-entropy, while level C benefits from focal loss. This proves that loss strategy must be empirically verified per subtask, not inferred from imbalance ratios alone. So what happens when we compare the 2 architectures? The cascaded system wins on accuracy across all 3 subtasks. The gains are modest for A and C, but a massive 7.1 percentage point macro F1 improvement on level B. Why? Because the joint model's shared encoder has to balance gradient signals from all 3 tasks simultaneously. On the most imbalanced and difficult task, this causes negative transfer. The shared representation gets pulled in conflicting directions, hurting stability and final performance. The cascaded model, by contrast, dedicates an entire independent head and loss function to level B, optimizing it without interference. But architecture choice always comes with a cost. The cascaded system uses roughly 3 times the parameters and incites 1.67 times the inference latency. The joint model is leaner and faster, but pays for it in accuracy, especially on class imbalance subtasks. The authors also run an end-to-end cascade evaluation, where the model's own predictions propagate through the pipeline instead of ground truth. They find that roughly 20% of the final errors originate at the very first stage. Once level A makes a mistake, the downstream models can't fix it. This establishes a hard upper bound on error propagation, inherent to the cascaded design. What does this mean for you building or researching hierarchical NLP systems? There is no absolute winner. You're looking at a quantifiable engineering trade-off. If your deployment environment is constrained by memory or latency, the joint multitask model with task gating offers a solid baseline with significantly lower overhead. But if you're prioritizing detection accuracy, particularly on severely imbalanced subtasks, the cascaded architecture's accuracy gains justify the computational cost. The key takeaway is that hierarchical modeling requires deliberate architectural choices, task-specific loss calibration, and rigorous error propagation analysis. Intuition alone won't cut it. If you're working on content moderation, multitask learning, or hierarchical classification, this paper provides a clear blueprint for how to structure your experiments and evaluate your trade-offs. I'll leave a link to the full paper in the description if you want to dive into the ablation tables and training dynamics. Thanks for watching, and I'll see you in the next one.